are the drift velocities, that is with the wiggle taken out, of the electron. So an electron that has just wiggling and no drift would have to be the one that was made at the point where the tangent to the ion curve has zero slope, right? That's right here where the electric field's at its peak. But that's exactly what we already knew. The electric field at its peak, you ionize there, the electron oscillates, but it doesn't drift. It moves back. Well, you see that. That's the zero slope electron. Also, it comes exactly back and kisses the ion again, one cycle later. Now, if it's made a little bit later, it will recollide. Of course, that's why you get high harmonics. But take a look at these recollisions. These are places where there's a very, very large difference in slope of the electron and the ion trajectory. Now, that difference in slope, that's the relative velocity of the electron when it comes back. You know, in the inertial frame, the ion's not moving at all. And all that velocity belongs to the electron. In this Kramers-Henneberger frame, they're both moving in our coordinate system, and they have different slopes. And it's the difference between those slopes that's that velocity. Okay? Now, think about rescattering. Think about elastic rescattering. Elastic rescattering is, you know, tennis ball off a wall rescattering. Okay? The wall is supermassive, just like our atoms. The electron's superlight, just like our tennis ball. And all that happens in one dimension, for sure, all that happens is velocity reverses. Well, I already figured out what its relative velocity was. So if I square that, I can find out what its initial kinetic energy is in that field. Okay? And then it continues to move in the field, but with a different velocity. And the analysis of this very simple sort leads to a kind of an interesting revelation about how rescattered electrons are. Depending on where they rescatter, they can produce very, very high energy electrons, much higher than the 2 UP plus 1 UP offset that we saw for the directly ionized electrons. In fact, this plot here shows along the bottom here are all of the electrons that bounce off on their first return to the atom. If they miss that first time and they come back and bounce off on the second return, that's n equals 2. If they go to the third time, that's n equals 3, and so on. You see a lot of really cool stuff here. First of all, you see this really nice even odd thing, okay? Where it's the odd returns that make the high energy electron. I think that's kind of cool. Also, the first return has the highest energy electrons. So we can really learn a lot about electrons. And so, by the way, if we start doing spectroscopy, we look up here at 10 UP, we'll be seeing those highest energy electrons. We'll also be seeing, according to the model, you could say, we'll be testing the model. We'll be also testing the model to see what the physics is of the first rescatter. When you look at the highest energy electron. Okay, now, let's move along, because I wanted to, what time is it?
For about half an hour. 6 minutes.
You have about half an hour.
Oh, 10 past?
10 past 6.
Good. I'm on 10. Let's get beyond single, oh, I misspelled electron. You see how sleepy I was? Let's get beyond single electron atoms. Very few single electron atoms in nature. Pretty much none of them come out of a bottle without doing something really special. What happens when you worry about the other electrons? Well, there are two main kinds of features that I want to concentrate on here. The first one is non-sequential multiple ionization. So you could imagine multiple electrons coming out for lots of reasons. After all, why don't we just go study that for a while? It seems like it's an extremely valid thing. Why is it like that? Let's take helium, for example. Both electrons have the same binding energy. They're in a degenerate 1s state, how come only one comes out? Interesting little dynamics question. Maybe we'll have a second question. Okay. Well, the answer to that question experimentally is that sometimes both of them do come out.
Yeah.
In fact, maybe it sounds a little paradoxical, but at the lower laser intensities, the probability that they both come out kind of in a concerted way, that is, they come out together, one coming out causes the other one to come out, however you want to talk about that, is actually quite high. And the reason that you know that that's true is because we have this beautiful agreement with either classical or ADK theory for ionization that we can compare to our actual ion yields. Now, I showed you that Steve Auk's paper from the old days where everything just matched. Absolutely beautiful. Well, along comes Lou tomorrow with his much more careful and patient approach, and he finds that, in fact, the ADK works really well for a single ionization of helium. The double ionization of helium, ADK would follow this inner curve here, inner part of this gray curve. So actually, if you get up to high laser intensity, above 10 petawatts per square centimeter, it kind of does follow ADK, but down here it sure doesn't. There's an extra process, a non-ADK process. And that's what Lou, maybe I'm not sure who coined it, but he probably was the person who coined it, might have been. That's what this so-called non-sequential ionization is all about. Now, it's been studied to death. It's been studied absolutely to death. In fact, it is no longer, I would say, a really hot topic for study, mostly, because it's been so much studied. And from all its characteristics, it looks like E2E inelastic scattering. It actually looks like it comes from those recollisions. It's one of the things recollisions can do. They can elastically scatter. They can also inelastically scatter. If they have enough energy, they can even ionize. And that seems to be contributing a lot of this population. Okay, something else that happens beyond single electron atoms, strong field ionization of inner orbitals directly. Not from rescattering, but directly. Okay? Now, this has been seen a lot in high harmonics. And I showed here some stuff from our own lab, but there's other people's labs who have done this, a lot of them. Paul has done it, for example. We've done it in other molecules. But the idea is that if you really look carefully at a high harmonics spectrum, so this is a high harmonic spectrum from a molecule, SO2, as you coherently move the rotational coordinates of the molecule around, I won't go into more detail than that, but you can just imagine I can look at this on this axis as rotating the molecule around in some certain funny way. This happens to be an asymmetric top, and so it's in a very weird way that it tumbles, but it still tumbles in some way that you can follow. You see that the high harmonic spectrum depends an awful lot on that instantaneous orientation. You can use that to match up different orbitals that might have been the ones contributing to the ionization and recombination. And when you do that, you find that actually it looks like it's pretty common for not the outer electron, but one of the other nearly outer but not really electrons, ones that are bound by a couple of EV, to participate and in fact dominate in high harmonic generation. Well, that's high harmonic generation. But, you know, if one electron manages to make a high harmonic, 999 contributed to the photoemission spectrum. So shouldn't we be able to see this in photoemission? Maybe. Maybe. There's some recent evidence of that. So now I've spoken about a number of different things. I haven't covered the entire universe of photoionization and strong fields. I've chosen some things that kind of fit together in this picture of above threshold ionization. And what we want to do now is kind of put it all together, because when you do an experiment, chances are you're not able to decide which of these things is happening. They're all happening. You know, you have to look at one or not. Okay. So here's a little simulation of putting it all together. This is just ionization of hydrogen, showing that the quantum mechanical wave shows evidence of rescattering. It shows all of the different dispersion of electrons coming out at different energies at different angles and different times. And we would like to do experiments that can capture that complexity. You know, not just these single narrow angle. Let's look at the whole thing. Okay? So we and many other people have adopted a kind of detector to do that called a velocity map imager. It's very simple. I'll explain it in a minute, but I just want to point out that it produces a momentum map or a velocity map. I don't know why it's not called a momentum map imager. Why is that? Someone knows.
Because momentum is serious. Velocity is not serious.
Velocity is not serious. These velocity map images produce these beautiful pictures. You know, every little wiggle here is real. I mean, some real physical phenomenon. These little spider legs coming out. And here, these are the Freeman resonances. Momentum increases away from the middle. And the polarization of the laser that was driving it is this way. So you can see most of the currents coming out here, but not all. You can see some rescattering way up there. There's a nice circle here, which turns out to be right at that 2UP place. Beautiful. It's all there. It's so easy to make, too. It's a two-dimensional imaging plate that you use electric fields to suck photoionized electrons onto the plate. And so you get a kind of a pancaking of the momentum component that's along this direction, but in the transverse directions, it's true, it's accurate, it's good. It gives you that thing. It's great. So the scale of this is set by the wiggling electron free momentums. That's the wiggle. That's the momentum maximum that corresponds to the power mode energy maximum. And in fact, if I draw a little circle exactly at that point, it really does correspond to where the current drops off very dramatically in my spectrum. Now, let's start taking a look at some cool things. One of the things we were sort of interested in, and other people too, is these electrons that come back and it seems like something that very often happens at these very low energy returns. Low energy returns are a big deal. And now we have a momentum map imager. We can look at low momenta pretty easily. We can blow this up as much as we want. So here's a blow up. This is argon. And this is just argon ionized in a Ti-sapphire laser field. There's absolutely nothing special. This is totally generic now. Okay? All we did is look really close at the very low momentum. And well inside the first ATI peak, you see other structures. And by now, at this point in the talk, you look at that structure, you heard about the Freeman resonance, and you say, man, if that isn't a Rydberg series, I don't know what it is. That's a Rydberg series. What is that? That's not an ATI peak. It's well inside. We're looking at really low momentum. What is that? What that turns out to be are auto-ionizing states that are caused by something that we always did know could happen. That is photoionization, not to the ground state of the ion, but to the first excited state. The first excited state of a rare gas cation is the fine structure split state. Linda has studied this. Actually, a lot of people have studied this, but not this auto-ionizing feature from strong fields. This is kind of new. And it's so distinct. In fact, what's interesting about it is that the width of these lines is so small. Here's EV. The width of this is 0.005 EV. That's less than the transform limited energy width of the laser that did the ionizing. But of course, that's not surprising because it's an auto-ionizing state. It's actually debris that's left over and hangs around for microseconds and then decays, or at least hundreds of nanoseconds. And that's what's causing those very narrow features. Okay, great. Let's see something. Oh, by the way, here it is in krypton, and it's just incredibly gorgeous in krypton. You can see the same thing. autoionizing rate. We saw it in argon first, spent a lot of time on that. Then went to krypton and we're just blown away. Okay, well, this gives us a way of studying the excitation process. The excitation process itself is pretty fast. It's field ionization. It's this thing it's an attoscience topic. We're not doing attosecond pulses, but the approach to excite these states as all of the ponderomotive shifting and everything is going on in the system is something that could give you access to attosecond timescale. There's a way to probe attosecond time. Okay. Now, a fundamental feature is that different drift energies ionize at different times. That was one of the first things I mentioned. Now I want to come back to it, just to remind you that's these slope differences here corresponding to very slightly different time differences. So with this velocity mapped imaging thing, can we tell anything about that? Can we actually measure it? In fact, as successful as this model is, I would say most of us experts, whatever we call them, people like Ken Schaefer, I mean, most of us are going to kind of doubt the validity of this idea that different electrons ionized at different times have different energies. Just because it works for recombination and atom chirp and all that doesn't mean it has much to do with what's going on up here. Why? Well, because it's really tunneling and you're asking the wrong question. It's not when, it's at what rate does, stuff like that, right? Okay, fine. Let's just look at an experiment. We can extract the dynamics by modulating the field with a second laser. So we add a second field let's see, I have to say this right. Look at this picture. We strong field ionize our system. That's this blue curve, oscillating electric field, right? And then we add a very, very weak half frequency field. And the idea, of course, is to make it so that sometimes that will constructively interfere with this electric field and make these peaks bigger while this one is smaller, that kind of thing. So it's a way of tweaking that phase a little bit, just tweaking the phase. This was our idea. That's why we were doing it. Okay? When you do that, this is what that VMI picture looks like. This is a truly tiny field. We're talking about something that is maybe the intensity of this beam is well under 1% of the intensity in the main beam. It means that the field is a few percent, less than 10%. Has a gigantic, super gigantic effect on which directions the electrons go and also on a lot of other stuff. If you want to think about this small field as being a little perturber, then on top of all this multiphoton ionization, you have a little single photon at half the frequency that can either promote an electron to higher energy or demote an electron to lower energy, and so you have two-path interference of those two processes. That's a way to kind of motivate your thinking about it. Of course, that's terribly oversimplified. That's terribly oversimplified. Nonetheless, there's some truth in it. Okay, here's the data again. This is shown in a slightly different view. And what we've done is taken this apart by integrating over this half circle and ask when does the current come out here, and integrating over this half circle ask when does the current come out here. And we can plot those as a function of time. And we see that these different ATI peaks and these little side pan peaks in between that come and go with phase all have different times, different phases when they add up. So now you begin to see the method here. We're really trying to find out if the low energy ATI peaks have a different phase offset from the high energy ATI peaks because they're produced at a different time, is the idea. Well, really what we're measuring here is something that is called in the business of Wigner delay. The idea of the Wigner delay is shown in this little animation. I wonder if it's going to repeat. Probably not. Okay. The idea is that When you ionize in the strong field approximation, you don't worry about the Coulomb field that is pulling back the electron. And of course, the Coulomb field is a big deal. It causes a change in the time that an electron gets to you. If it has a certain energy, it becomes potential dependent. A free electron, actually, it's a little paradoxical, but this picture made it very clear. A free electron gets out slower than a bound electron. You might think a bound electron is going to get out slower. But no, what we're doing is comparing two electrons that have the same final energy. So then the bound electron gets here faster. All right, fine. So we plot that. All we're doing is plotting where these peaks are as a function of ATIP. And what we find is that the even and odd peaks are pi separate. That's actually what we expected. This is a strong field approximation result. But there is a very, very strong intensity-dependent effect for the low energy peaks. Okay? And this is a real view. It's not what I would call a transparent view, because you have to deconvolve the entire process of ionization. But this really is showing you that distortion of the Coulomb potential, the intensity dependence, the fact that this curve doesn't look like this curve, and all I did was cut the intensity by 4. It shows the effect of the distortion of the Coulomb potential. So our idea is that we're going to kind of play around with this now and see if we can use this to understand the physics of field ionization. Okay. Finally, I'm going to end up with something, because Lou tomorrow is going to talk about laser-induced electron diffraction. And it's really just a couple of slides. I know it's late. But remember, now you've got a pretty good picture in your head of what these velocity map images look like. And I've shown you krypton, and I've shown you argon, and I have steadfastly avoided showing you a molecule, and now I am. I'm showing you molecules of nitrogen. Everything else is the same, 800 nanometers. It's all about the same. And it kind of looks the same at first. It has this circle, but has something else as well. It has these two other circles. It has one up here, and it has one down here. And see, I'll show you that again. You can see them by eye. Okay? And the notion that Lou, and also we, are now following up is that this is caused by not just attosecond rescattering, which happens in the atom too, but attosecond rescattering from a molecular potential, which produces molecular diffraction. In addition to atomic rescattering, you now have diffraction. Some momenta would like to scatter more than others. He wrote a Nature paper on this in 2012 and got us all excited. Here's something from that paper, that Blaga paper, that shows the physics of what's going on. Let me go back to this picture first. That this circle is a scattering ring. I'll show you in a minute that it really is. A scattering ring happens when you take a quantum mechanical projectile like an electron and send it through a gas that has some non-trivial potential, like a molecule that has multiple atoms in a particular relationship to each other. They'll diffract the electron more efficiently into certain angles because of constructive interference between the different centers. Now, the weird thing in the strong field case is that it seems like if I have a beam of electrons, I should see that scattering ring here, right centered on zero momentum. It's an equal momentum in all directions. But instead, I saw it up here and down here. And this is really what Demaro and Blaga explained. They pointed out that it's because that rescattered electron is still in the laser field. The same thing that makes the 10 UP happen, because when you rescattered, you were still in the laser field, and you had to accelerate more in the laser field, right? That same phenomena shifts all scattering off of the molecule, either ionization or rescattering, by 2 UP, or in momentum, by A naught, by the vector potential, the peak vector potential. And so there's that circle around the peak vector potential. He was doing this with infrared, and there are different things that are different from our experiment. But he points out, for the first time, I thought, that centered right on here is where you should see the scattering rings. And of course, since it's linearly polarized, centered also here should also see scattering rings. And so that's really what we were doing. Now, we've been playing around with this. One of the cool things is that we can align nitrogen molecules. We know how to do this, everybody else does too. Well, those scattering rings are much more prominent when the molecules align with the polarization known as anti-aligned. That's an interesting fact. We've also, we've taken a look at these beautiful pictures and we said, if I really care about this ring, there's got to be a way of getting rid of all of this. One man's signal is another man's background, So there must be a way of getting rid of all this other stuff by finding the correct basis set to project my electron patterns on. I want to know about patterns that are centered here. I don't care about patterns that are centered here. So I should do some kind of a Legendre polynomial decomposition, a projection of my data. You guys are theorists. I'm sure you immediately get the idea. You can find a basis where the information you want is sparse in that basis, and that's your basis. So actually, we've done that. So if you do that, this ends up being that scattering ring from nitrogen. And I challenge you to compare that to anybody's electron beam experiment. I mean, these things are as good. Well, there are some caveats here. It happens in a strong field. It has to be a molecule that you can do that with. But you make beautiful patterns. So we're now trying to explain this. Okay, I'm done. So most of the electrons in strong field ionization never make high harmonics. That's the first take-home message. The second one is that their spectra reveal the dynamics of the strong field laser atom interaction. You look at their spectrum closely. The more you look, the more interesting subtleties you can find out about that interaction. And now that we've extended it to molecules, we may even also have new methods to probe structure and dynamics on this attosecond angstrom timescale that so much of the workshop is devoted to. Thanks very much, and I'm really happy to get a discussion now or at the close.
Questions?
In your last slide, how did you get it so clean? I'm not clear how you removed it.
I thought the theorists would pick up on this right away. It's a Legendre filter.
Yes.
So what you do, typical Legendre filter, which we use all the time, a lot of people use it, is that you end up with a VMI image that's all kind of speckly. But those speckles, those are just Poisson fluctuations of particles hitting. What you care about is the pattern that you would see if you collected an infinite number of electrons, right? All those speckles and the Poisson fluctuations got small compared to the signal. So one way you can cheat to get there faster is to project your data onto a basis of Legendre functions for each radius. So you divide this into lots of little radii, lots, like hundreds of little radii. And at each radius, you have some signal. You project that onto Legendre functions, P0, P1, P2, P3, up to P10, up to P50. At some point, you cut it off. You'll be able to see where it gets cut off. There's actually a nice knee. And then all that other stuff is noise. And so then you just plot it, and you just plot the Legendre coefficients rather than the individual little speckles.
Why don't you see two rings? Because I
You do see two rings. I just showed one. If that's the question. We just blew up this area right here. There are two.
So that's
Yeah.
tensile.
Yes.
I have a question regarding your orthogonizing signal. You have this signal at low energy from a process where you have a decay to an excited state in the atom, right?
Oh, you mean the low momentum?
Yeah, the low
Yes.
momentum, the low energy electron
Right.
emerging from the...
Those are very, very low energy electrons. So what happens is that, we did a couple of experiments back in the 80s that spoke exactly to this problem. If you can do above threshold ionization, for sure, you're also trapping some population in bound states. Now, the population that is most readily trapped is population that has bound state Kepler orbit times that are longer than your laser